Hello everyone. In this video we are going to review chapter 7, which is permeability of soil, and chapter 8, which is seepage through soil. So basically we are not going to cover the whole chapters, either chapter 7 or chapter 8. Just try to focus on the problem what we are going to do today. So let's try that one, and I posted that worksheet in your blackboard, also the solution there, and now I will explain each of the problem here so that you can understand that one easily. So the first problem here is for a constant head permeability test. So they gave you L equal to 30 centimeter. Area of the specimen, which is 177 centimeter square. Head difference del H, or sometimes we call that one H, which is actually 50 centimeter, and you open that valve and you will collect Q is equal to 350 centimeter cube in 5 minutes. So T is basically 5 minutes. Now let me show you the constant head test, setup, so that you can understand which one is what here. So basically this one looks like this. So this is your soil specimen here. The length of this one is basically 30 centimeter. The area of this, this is a cylindrical shape specimen. So the area of this one is 177 centimeter square. You collected water here, which is basically 350 centimeter cube in 5 seconds, and that's the difference in head here. That's actually your H. So this one is called constant head test because this head will be always constant, even though the water is passing through that specimen and collecting here, but actually we supply water here, and there is a drainage system here. If you add more water, the head would be always here. Now, we know that hydraulic conductivity is basically QL divided by AHT. So all of them are actually given here, so I can plug that one here. 350 multiplied by L 30 divided by 177 into H equal to 50, and time T is in minute, so if you try to change that one in second, then you have to multiply that one with 60. So this one will give you the K value of 3.95 into 10 to the power minus 3 centimeter per second. So basically the answer would be 4 into 10 to the power minus 3 centimeter per second, B. Okay, now let's move forward for problem number 2. This is actually problem number 1. For problem number 2, we have to draw the diagram here. This one is showing a angle system, and if you take the let's say here is the head here, here is the head here. The difference between head H is basically 4 meters. The distance from these two is S. So the distance from here to here, actually your L, because your hydraulic head difference is from this point, and this is the distance from this point to this point. So actually you can find out your L from here. So L is equal to S divided by cosine alpha. So that's basically your alpha here. Okay, so you can see the distance is here. That's actually your L, and this is your alpha. So L is equal to S divided by cosine alpha. Now they also gave you this distance from here to here. This one is 3 meters. Now when you try to find out the area, actually you have to find out the area perpendicular to the flow path. Okay, perpendicular to the flow path. So the flow is going along this direction. So the area would be this multiplied by, let's say this is L here, and this angle is alpha here. So L is basically H1 cosine alpha which is 3 cosine 8 degree, alpha equal to 8 degree here. Now the question they are asking here that to find out the flow rate through the layer per meter length. per meter length means like the length perpendicular this way. Okay, so what's the area of flow? So this multiplied 1. Okay, in this perpendicular direction is 1 unit, and this is your L. So basically A is 3 cosine 8 degree multiplied by 1 in the other direction. Now we know that Q, flow rate Q, is equal to K I A. Now K is given, which is basically 0.08. I is equal to H by L, and area is basically 3 cosine 8 degree. So if you solve that one, because H is 4 meter and L is S divided by cosine 8, means S is basically 50 meter. So if you plug that value here, then you get 0.19 into 10 to the power minus 3 meter cube per second per meter length of this way. Okay, so basically your answer is B. Your answer is B here. Okay, now let's move forward to problem number 3. Three is a little bit difficult to draw in this board, but still I'll try to do that one here, because without the drawing it's very difficult to actually explain. So problem number 3, 3, 4, 5, 6. Actually there is a mistake here, like there is no 4 here. So it should be 3, 4, 5, 6. So if I do like problem number 3 here, we have water here, this side, and the elevation of that side is 193.3 feet. This side elevation is 260.3. That's basically, there is a sheet pile here. So water is going to flow like this. So this is your flow, and it looks like this. And here is This is impermeable layer. So since the head here is lower than this one, so water will try to go like this. So each of that path we actually called, like you can see, this is 1 path, 2 path, 3 path, and 4. We call that one number of flow path. So NF, which is actually 4 here. Number of flow path, 1, 2, 3, and 4. Now you can see here they put a lot of points there. These are actually, let me use a different pen. Actually, I have more here. No, actually, I made a mistake here. Let me do it again. So there is basically 1, 2, 3, 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, 8. And then you have so what they are trying to say that the head at point 12. So point 12 is basically here. So these are called like equipotential line, means like the head here, 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 and here is same. And these are called flow lines, the water will flow along that line. So this is your nth number of flow line. And then number of equipotential drop, that's what we call that one, that how many drop we have here. So you can see here the first drop, actually this is your water level, this is your soil layer here. So you usually follow any of that path here and try to see that how many drop you have here. So we call that one equipotential drop. So first drop would be actually here, not this one, okay? Drop is equipotential drop. So I am measuring from here. The first drop is here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Actually, there is 17 here. I missed one of that point here, I guess. The bottom line is actually you have to count every time from not the first one. The first drop is actually this. First drop, second, third, fourth, fifth, sixth, seventh, eighth, 9, 10, 11, 12, 13, 14, 15, 16, 17. The last one would be actually on the soil surface on the other side. So the equipotential drop which is equal to difference in head divided by the number of equipotential drop. So this is 17 here, okay? Now, if you see the head difference, which is actually 260.3 minus 193.3 divided by 17, which is actually 3.94 feet. So what will happen, actually, if you see the head here, you already know the head here because you know the height of water here. So what you have to do to find out the head at point 12, so how many drop you have at point 12. You can see 1 drop, 2nd drop, 3rd drop, 4th drop, and 5th drop. 5 drops. So basically your head at point 12 would be this head 260.3 minus 5 drops, and each of them is 3.94, which is basically 240.6 feet. So if you go more, then basically there will be one more drop, means like 240.6 minus 3.94. If you go here, then basically this point, then it's 2 point after 12, so that would be 240.6 minus 2 into 3.94. That's the way it goes all the way, and then you will see that when you are there, then basically your head would be 0. Anyway, let's try to do the next one. This one is also, the next one is actually should be 4, but actually here it's 5, but very similar problem. This one is saying that the flow net for the flow of water through the soil below a 5-meter long hydraulic structure is shown below. The flow net is shown here, okay? Very similar one. So this one would be easier to draw because they don't have that many flow lines here. So this one is basically 6.3 meter. So if I draw the equipotential line here, and the flow lines so first of all they're asking like what would be the actually here this is your point O. Now what would be the head here? Similar to the other problem, you can see here is your head is actually 6.3 meter. That's the difference from here to here. That's actually the same thing here. And then we have to see that how many equipotential drop we have here. So if I follow this one, then this is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So a total 10 equipotential drop. So each of the drop would be equal to equipotential drop would be 6.3 divided by 10, which is equal to 0.63 meter. Now they are asking actually the hair. Now it's very difficult to see that this one is along this line here. But you can see this is equipotential line. So basically the head here should be equal to the head here. Let's say this is point P here. So head at O should be equal to the head at P because they are on the same equipotential line. They have the equipotential means like the same head. Now if you try to find out the head here, then you can see how many drops you have. 1, 2, 3, 4, 5, and 6 drops. Okay, 6 drops. So basically your head at O is equal to 6.3 minus 6 into 0.63, which is actually 2.52 meter. So the answer is actually B here. Okay. Now they're asking like the next question here. This is number 5. But for problem number 6, they're asking that there is another point here which is called F. And if you put a piezometer here, then basically you will see the water is not along that line, this one a little higher than that. That we call that one H1 here. But what would be your H1 in that case? So we'll try to find out what is the head at this location here. Okay? So that's actually problem number 6 here. So head at F is 6.3 minus how many drops here? 1, 2, 3, 4, 5, 6, 7, 8 drops. So this one has to be 8 here. And in that situation, that will be 1.26. So that's above this water level here. So this one has to be 1.26. What about here? That would be 1.26 minus 0.63. So that's actually 0.63. And what about the head here? That would be 0.63 minus 0.63, that would be 0 here. So actually if you see the water line is here on the surface of the water, actually your head is always 0, right? So that's why this one is 0, this one is 0.63, this one is 1.26, this one has to be 1.26 plus 0.63 and so on. Okay, that's the way we try to find out the head at each of the nodes. Now let's try to do the last one here, which is number 7, based on the same figure here. This one is asking that if the hydraulic conductivity of the soil below the structure is 2 into 10 to the power minus 3 centimeter per second, the flow under the entire structure per day will be how much? How many meter cube per day? Okay, so you can see this is the soil here, and the hydraulic conductivity of the soil K here is 2 into 10 to the power minus 3 centimeter per second. Now we know from the flow that Q is equal to K H NF by ND. So K is the hydraulic conductivity, H is the head difference, NF is the number of flow path, and ND is the number of equipotential drop. And this one will give you Q, that's actually the volume of water that passes per time through 1 feet in this way. Okay, 1 feet in this way. If you multiply, you know that this one is actually 5 meters in this way. Okay, so if you want to get the total Q here, then you have to multiply that one with L into K into H and F by ND. So which is actually 5 into 2 into 10 to the power 5. I change that one from centimeter to meter, so that's why this one is not 10 to the power minus 3, that's 10 to the power minus 5. Number of flow path is 1, 2, and 3. And then, oh, I forgot to write the H here. So H is actually 6.3 meter, and then 3, total number of equipotential drop is 10. So that would give you your Q, which is actually 16.36 meter cube. But you have to remember one thing here, that since this one is per second and we are trying to find out the flow rate per day, so you have to convert that one per day. Okay, so if you convert that one per day here, then basically you can see that would be 2 into 10 to the power minus 5 meter per second, and 60 second per minute, 60 minutes per hour, and 24 hours per day. So that's basically that many meter per day. So if you plug that one here, then basically you will get that meter cube here. I'm just trying to consistent with the unit here. Okay, so that's about it. If you have any question, please Skype or FaceTime me to explain that one a little better. Thank you so much for your attention.